Greetings all, and welcome to another Kinematics and Dynamics of Machine video experience. Today we're going to be doing sample problem 8.2 from the Kinematics and Dynamics of Machinery book by Charles E. Wilson and J. Peter Sadler. Sample problem 8.2 is a planetary gear train analysis via the formula method. So let's get started. First off, let's take a look at what the system consists of. This is a schematic view of a planetary gear train. You can see the ring gear, designated with the R that I'm tracing along right now. Its gear tooth interface, designated by these two horizontal parallel lines. A planet gear, designated with the P. It is rotating in a bearing which is attached to the planet carrier, designated by a C, and it is also meshed with the sun gear, shown by these two horizontal lines, and then the shaft here. So as you can see from the schematic, we are only showing a cross-sectional representation of half of the gear train. We have one shaft here for the sun, one shaft here that would be on both sides for the planet carrier, and one shaft here for the ring gear. What we have, what we're trying to solve, is the speed across this gear train. In order to do that, we need a couple of things. First off, we're given that the number of teeth for the sun gear is 40, the number of teeth for the planet gears is 20, the number of teeth for the ring gear is 80. We're told that the sun gear rotates at 100 revolutions per minute, or RPM, in the counterclockwise direction. The ring gear rotates at 300 revolutions per minute in the clockwise direction. So note that they are turning in opposite directions. What we're going to do then is find the speed of the planet carrier, and we'll use the formula method. First, a couple of things that we should designate immediately. Let's go ahead and state, just as our starting point, that we're going to call the sun as the input for the system, and we'll call the ring the output. This is an arbitrary thing, but we do need to have some kind of starting point in order to perform the analysis, so it's entirely reasonable to state that. We will also state that clockwise will be the positive rotation direction. Therefore, we can immediately say that this 100 revolutions per minute counterclockwise can be designated as negative 100 revolutions per minute. Alright, so how do we solve such a thing? Obviously, we do first step 1, don't panic. And step 2, let's review some of the relevant formulas that we may need to do this. If you refer back to sections 8.4 in your textbook, you'll find a couple of things with regard to planetary gear systems. First off, we have the concept of the gear train ratio as expressed for planetary systems. This is equal to the product of the driving gear teeth divided by the product of the driven gear teeth. And it is positive or negative depending upon whether the spin direction of the driving gear teeth is the same as the driven. We also have the concept of the relative velocities of gears. The relative velocity is just equal to the velocity of a gear, subtracting from it the velocity of something else in which we're interested. For both of these sets of equations, the gear train value and the relative velocities, we add this little asterisk to indicate that we are holding something stationary in our minds as we do this sort of analysis. In this case, what we're going to do is hold the planet carrier stationary. When we have the relative velocities of the gears, we can get an alternate expression for the gear train value. It's equal to the relative velocity of one of the gears divided by the relative velocity of the other. Normal practice indicates that we call the x our input, and that didn't work out quite right, did it? That's better. And we'll call the y our output. So let's see how this works in practice. I'm going to start out with the gear train value. So the gear train value, R asterisk, as we said, this is equal to the product of the driving gear teeth over the product of the driven gear teeth. We've said that the sun gear will be our input and the ring gear our output. So the driving gear teeth will then be the number of teeth on the sun gear. The driven gear teeth will be the number of teeth on the ring gear. So this is going to be equal to 40, number of teeth on the sun gear, divided by 80. One other thing that we should note, and I urge you to pause the video at this moment and think about the type of ring gear system we're looking at, or the type of system we're looking at, is that the sun gear and the ring gear will turn in the opposite direction. So this is going to be a negative value. Obviously this is equal then to negative 0.5. So there's our gear train value. If we look at the relative velocity concept, we can now take a look at what the relative velocity of the input and the output would be. So we said we're going to, and I see that I have messed something up here. We need, no I didn't, hooray. We need to look at these relative velocities of gears. We'll go ahead and start with the output. So n sub y, don't forget our asterisk, is going to be equal to the output speed of our system minus the speed of the planet carrier. In this case, the output speed of our system is 300. Going back up and looking at my ring gear, which we already said was output, it's turning positive 300 RPM. So 300 minus the speed of the carrier for the relative velocity of my input. This is going to be equal to negative 100 minus the velocity of the carrier. So that tells me that the alternate method of getting my gear train value which is equal to the relative velocity of the output divided by the relative velocity of the input, is going to be 300 minus n sub c divided by negative 100 minus n sub c. So this is interesting now. I have two ways to get my gear train value. One of the ways allows me to generate a numeric value for my gear train value. The other way gives me an equation that relates the carrier speed to my gear train value. So this then implies that my previous value for that gear train actual number is equal to the expression that I had for the gear train value. At this point, it's every engineering student's favorite thing, a plug and chug exercise. I think that I can probably leave this in your capable hands and just at this point give you the answer, but I would urge you to go ahead and multiply this out, make sure that you can get the correct number. You should find then that n sub c is equal to 166.7 revolutions per minute. So there you have it. This is a fairly easy example. The method itself is not difficult, but it is important to kind of think through it. It oftentimes is helpful to have a planetary system in your hand so you can rotate the gears and see what happens if you designate one thing or the other as the input or as a fixed value. I would urge you to also take a look at the crib sheet of formulas for planetary systems that I handed out in class so that you will be able to verify that you can get the same number using that way. As with all of these, the most important thing is don't panic, and the second most important thing is find a way that works for the particular system you're looking at. Thanks very much, and I'll look forward to seeing you at our next class.